All right, so here we're getting to the core stuff of the framework, where we have a real logic theory. Then that you have three components essentially. So you have knowledge about the grounding of the symbols, all of the stuff that we've been talking about for domains, constants, variables, everything. A set of closed logical formulas describing factual propositions and general knowledge, like I've also been mentioning, and also the operators and the hyperparameters used to evaluate the formula. So all of this stuff is encoding the knowledge in your theory. And learning and reasoning in these kinds of theories are both associated with searching for and applying the set of values of parameters from a hypothesis space that maximizes satisfaction, as Paulo mentioned just now. So let's see what that looks like. It's not surprising that what we're going to do is define an optimization problem, right? So we aggregate the truth values of all the formulas, and we select a formula aggregating operator, just called SAT-AG, where you take all of the possible formulas. This is just a clean start for the one for each formula, and you'll have your value saying, okay, this is how satisfied your theory is. So learning then is the process, as usual, of searching for the set of parameter values theta star that maximize this satisfiability with respect to a given aggregator. So SAT-AG now is what you're using to evaluate, and all you have to do is come up with a good enough or an optimal value for this set of parameters. So now that we have this general formulation in place, you can learn the grounding of constants, functions, predicates, simply by learning the grounding of constants. Just this corresponds to learning of embeddings. The learning of functions corresponds to learning generative models or regressions, as I mentioned before, and predicates correspond to learning a classification task. Querying, on the other hand, now allows you,
Just clarify on the last slide. So it's only with respect to constants, functions, and predicates that there are parameters. Is that correct?
Yeah.
So just one thing that this is where you start to see the difference between LTNs and LNNs, where they're pushing the parameters down at that lower level, whereas the LNNs, they don't do that. The parameters reside with the operators.
Right.
Sorry about that.
No, that's okay. That's a good clarification. All right. So for query answering, you can check if a certain fact is true or how much it is true, and you can do several types of queries. So truth queries, what's the truth value of a formula? When I say fact, I mean a whole formula, right? The truth value of a formula in the language. So if the formula is closed, as I mentioned several times, we have to have like a single truth value, so a scalar. And if it has n free variables, we get a tensor of order n, one. So all the possibilities for the n free variables. The value queries for terms is the same kind of thing. Instead of for a formula, I'm just talking about a term. And also we have the same kind of thing for generalization truth queries. What is the truth value associated to a formula evaluated over unseen data? And the same kind of thing for the value queries. So this is what we're now seeing, that you can generalize the kind of things that we do in machine learning at the data level. Now you can generalize and do the kinds of things that, for instance, are done in relational learning as well. Reasoning is then the task of verifying if a formula is a logical consequence of a set of your theory. So if you have your formula phi, and all you have to do is check if it's a logical consequence, is if all models of your theory gamma is also a model of your formula phi. So you can generalize this in real logic, because if I say that something holds, you have to fix a threshold, right? So you define the interval q from q to 1 with q being at least 0.5, and you assume then that the formula is true if and only if the truth value is in this interval. So this sounds great. It's in theory, it's very, very tidy, but unfortunately, the definition requires inspecting potentially infinite sets of groundings. So how do we do this? The authors in the paper propose two options. There might be others, but the first one is called querying after learning. So you consider only the grounded theories that maximally satisfy the given theory, and you can find a probably likely incomplete set of grounded theories via multiple optimization runs. And in this case, you get a kind of brave reason. We'll see how this can fail pretty easily in the next slide. And the other one, more closely related to how things are done in, for instance, logic programming or kind of computational logic that's implemented, is proof by refutation, where you say, okay, I'll look for a counterexample to what I'm trying to say holds. And if I can't find it, I'll say that it's assumed to hold. The general formulation of this, unfortunately, cannot be used as an objective function because you get null derivatives. But there is, in the paper, they develop a soft variant of this, so you can do it. So the example is you're trying to see if your theory models this. So if you have, in your theory, you have A or B, you want to see if this models A. This, of course, is not true, because A or B, it could be just B, and that'll be fine. So that's your counterexample that you're looking for. And on the top, we have several runs where you see that things they converge in such a way that they miss the counterexample. But when you do refutation, you see that the counterexample holds. So I don't have time to look at to go through the details of this, but this is quite direct, a quite direct illustration of how things how the option one might fail. So the use cases, I'll have to go through these quickly. At least the first one is interesting, but also I include several links for each. So the sources, I include links for the GitHub repository of Logic Tensor Networks, where they have several Jupyter notebooks. Here in this case, I have the full example here, and in this case, the data is from a well-known repository of data, and here they're trying to do multi-class, multi-label classification of a kind of crabs, where they have 5 morphological features. So in the paper here, they don't say exactly what they are, but here I put them here for you. The kind of things that they measure, the frontal lip of the carapace in millimeters, the body depth, several, measures of these crabs, and they are labeled both as male or female and as blue or orange. So that's why it's multi-label. So you have a predicate that classifies points into labels using a neural network, because there's a lot of data on. I think they measured 50 crabs that they measured, and you have all the values for each one. And you can query, for instance, the satisfaction level of some formulas. Like maybe you have a hypothesis and you say, hey, does blue mean it's not orange? Or maybe they're a little bit of both. So you say for all x, if you have that x is blue, then it is not orange. And the theory that they learned has a satisfaction level for this formula of 0.92, which means that this is quite generally true, but there are probably some counterexamples. And maybe you have another hypothesis that says things like all blue crabs are not male, which is what it's saying right here. And you see here that it's quite low satisfaction. So again, you can have a look at the more details in these sources. Another one, which I'll only say a couple of things about, is clustering. You can also do clustering with this kind of thing, where you have, x, the variables are the points, a C for the cluster labels. So there's one label for each cluster that you'll find. And the predicate, capital C, classifies points into clusters using, in this case, a neural network and some kind of axiom that you want to hold, because what you're trying to do is clustering. Here it says that for every point there exists a class that will have a cluster assigning that class to it. So this is basically, you have to cover all the points with your clustering. And this is kind of a dual. For every class, you have to have a point inside, so you can't have spurious classes in your clustering. And this is saying the properties. Here you have an example of guarded quantification, where you say for all classes C and pairs of points x and y, if the distance between the 2 points is less than 0.2, then you'll have that the clustering is assigning the same class. And if the same thing, there the distance is greater than 1, it has to have different classes. Okay, so it can't have the same one. So this is again an interesting application, because you might want to have some other properties, and the way this ends up working is that the theory will find the best way to satisfy all of these things at once. So this one I'll only briefly mention because I'm running out of time, but it's a pretty nice development of the smoker friends and cancer example that got started in the Pedro Domingo's paper on Markov logic networks. And we also, when I covered this in class, we mentioned it as the running example as well. So we have groups of people. They're in this case divided into 2 groups. There's complete knowledge about their smoking habits, and there is complete knowledge in the first group about who has and who does not have cancer. And knowledge about the friendship relation is complete within each group, but assuming symmetry. So if XY means that also YX are friends, otherwise the friendship is incomplete. And then we have another set of formulas that we have encoding knowledge about smoking, friendship, and this disease. So smoking causes cancer, for instance. Friendship is normally symmetric and anti-reflexive, so you're not friends with yourself. Everyone has at least one friend. And smoking propagates actively or passively among friends. So you can evaluate all these things, and this is the kind of setup that you have. Remember that you have full knowledge about who smokes and who doesn't. So here, yellow is true and purple is false, or in between, you can have in between values as well, but here you have the crisp values at the beginning. Here we have white boxes because we only have complete knowledge of cancer for one of the groups, and also who's friends with who. Okay. So after training, then we can test satisfiability of the axioms, right? So here we have something like smoking causes cancer. We see that it's not, in this case, we have individuals that are not that are smoking and don't have cancer, so they're counterexamples to this. So you can issue queries with new formulas, like the other way around. What if, is it true that for all people P, if that person has cancer, then they also smoke? In this case, we can see that it's almost totally true. And something like for pairs of people, if either one of them has cancer, then they're friends. You can see that this has a very low satisfaction value. So this illustrates quite nicely what the kinds of things that you can do. You can also visualize the embeddings, because this allows you to do things like compare, say, okay, these, like the blue ones are in a group, and you want to see if, I don't know, if they all smoke. In this case, you see that they don't. So these two do smoke, and this green one has much lower value for smoking, that kind of thing. And also the friendship relation and the cancer degree. So finally, I probably won't be able to get to the bonus material. I'm already out of time, but I wanted to, as we did with LNN's lecture last time, let's see where this formalism lands within the Kautz taxonomy, and it falls within the neuro, sub index symbolic category, where these are the kind of architectures that transform symbolic rules into templates for structures within the neural network. So you have first order logic, you move to tensors, you have your neural models, you get your tensors back, and then you move back to first order logic. This is just a capture from the structure that is shown in the paper. And one question that one might ask is, how is this different from category one of the lowest one, which is symbolic, Neuro Symbolic? Here, only in that category, only the objects or the individuals are tensorized. And that's just the standard way in which deep learning approaches work, right? So after processing the input tensors, they get they produce output tensors, and those are transformed back into symbols. LTNs, on the other hand, they tensorize all logical components, right? So objects, predicates, functions, and formulas. And there's this newer classification or categorization that kind of extends Kautz's taxonomy, where they look for templates. So you have the paper down here, where you can see that because LTNs jointly minimize neural network loss functions and maximize first order logic theory satisfaction, this can be seen as a kind of semantic loss function, where you want, this is the kind of like, I'm tying the bow on all of what I've been saying throughout this lecture, where you're trying to make sure that your loss function captures the knowledge that you want to represent as best as possible. So unfortunately, I don't have time to go through this, but it's simply a little bit more about the details that you have to make sure are in order, so that you can actually do gradient descent and actually learn all of this stuff. And you have the vanishing and exploding gradients that we saw also in the background material, and just a way of fixing this, where the authors propose a stable configuration where it just get rid of these problems, just by doing a little bit of um, of math, essentially, right? So, if you avoid some sticky edge cases, then and you choose your functions wisely, then all of this is possible. Thanks for your attention.
All right. All right, that's it for today. We're out of time, and I gotta get to